All right, let's go through a few of these homework questions for lesson 26. So this one says the height of a pendulum h in inches above a tabletop t seconds after the pendulum is released can be modeled by the sinusoidal function shown below. All right, so we're given this function, right? So now it says the height of the pendulum at the moment of release to the nearest tenth of an inch is. All right, so if we're looking at this one, really what we're saying is that the time would be, well, what would the time be there? The time would be 0, wouldn't it? Oh, 1 sec. Yeah, so in this case, we're looking for when t is equal to 0. So we could actually just plug this all in, right? We could actually plug this in as h is equal to 4 times sine, and then 3.84 times a time of 0 would be 0, right? So all I would have left is this. So that would be 0.63 plus 8. Okay, so I'm going to show you this method, and now I'll also show you the graphing method too, because sometimes that can be more visual. So that'll be this case. So I'm going to put in the 0 there. So I'm just going to graph what's left right after I make t equal to 0. So if I put that in, I'm going to get sine, or 4 times sine. So it's 4 times sine, and then we're just left with 0.63. Close the bracket. And then plus 8. Okay. So we end up getting 10.35. Now, one thing, like if you punch that in and you got something completely different, one thing I want you to notice is you need to go to mode, and then make sure you're in the right unit for your angles. So if you go down here, you can see that I've got radian and I've got degree. This would be in radians, right? So when you're putting this in, this would, like, unless it kind of actually shows like you've got degrees in there, we need to make sure the calculator is in radians. So if you're getting those wrong, or a bunch of them wrong, that might be the culprit, okay? So your answer here would just be 10.4, right? Okay. Oop. Erase this. Okay, so now while we're on this, I would also like to show you how this would be the same thing as, well, it'd be the same as your y-intercept. You know what, we'll run into other ones too that we need to find, but here, let's kind of sketch that out other than actually graphing it. If you graph this thing, you'd end up getting, something where this thing, like, went up and then, like, crossed there and then back down again. When the time is 0, it wouldn't cross like that. That was a bad picture. But where the time is 0, right, that's going to be the height of your pendulum. So that would also be the same thing. That would also start at 10.4. So that'd be your y-intercept of your graph, right? Okay, so let's do some more. All right, so now if we're looking at this one, it says the height above the ground of a rider on a Ferris wheel can be modeled by the sinusoidal function, and then they just give us the function, where h is the height of the rider above the ground in meters, and t is the time in minutes after the ride starts. Okay, so based on the sinusoidal function, the maximum height of the rider above the ground to the nearest meter is. So I pretty much need to graph this thing to solve for this. And again, you got to make sure that your calculator is in radians, even when you're graphing, because if you're graphing and it's in degrees, you're going to get something kind of funny. So here, I'm just going to pause it and then throw that into my calculator. So you do that too. So throw that into your calculator and pause the video. Okay, so I'm going to plot this now. So we've got 4. Okay, so I just put it all in. I didn't want to take the time in the video to do that. So just make sure that if you're graphing this along with me, make sure you get the same thing, right? So can you graph this as well? Even if your numbers are different, right? Just graph mine, and then we'll see if we get the same thing. So now if we go graph, we should start seeing a bit of a sine wave. But you might notice nothing happened. It's still thinking. I can see that this thing is actually still drawing, but the problem is it's not actually drawing on my screen, okay? I need to either go like up, or I gotta go down, or left or right, or something like that, right? But I know this graph goes up and down, right? So it's not that I need to see farther to the left or farther to the right. I probably need to see either farther up or farther down. Well, do you remember how this number on the end, this plus 15, that is my midline, right? This thing is going across 15. So I got to see at least up till 15. But to see the max, I'm going to have to see up to the midline. And then I'm going to have to see up, at least the amplitude higher than that. So the top of this thing is going to be 15 and then another 4. Okay. And I don't know why we even had to graph this thing. I was being kind of silly because now that we do that, I've kind of explained that. So let's look up. I'll just show you what I mean. So if we go window, and we're going to go up till 25, right? That should be enough. So we'll go Y maximum down to 25. So Y maximum at 25. And then there's our graph, right? There's that wave we're looking for. Okay, now, again, I'm going to feel kind of silly here because I'll show you how we can find that peak, right? We can find that max, but we can actually see it just from looking at the graph too. So let's go trace, not trace, we're going to go second calculate, and we're going to find the maximum, so 4. And then, yeah, we can actually just kind of go to whatever maximum we want. The maximum height of the rider above the ground of the nearest meter is. So, yeah, so we'll find maybe there, right? So it says left of the maximum, and then to the right of the maximum, and then we'll take a guess. And we end up with our Y value, which is the one we're looking for, right? The height, because this is our height up and down. Our Y is 19. Now, I was just saying that we didn't really need that at all, did we, to figure that one out? Because if we look at this, our midline was at 15, right? That was at 15 high. And then I can also see from my graph that 4, right? That means it's going to be, the period is going to be 4. So that has to be my 15 plus another 4. So the maximum value here has to be at 19. So that's what that would be. But it's good practice to craft these things anyway, right? We might need to do something else. All right, so this will be a good one. So let's do this one. And again, we'll graph it. So we'll go back here again. I'll delete this one out. Okay, and here, you know what? Let's actually read this first. So it says, the height above the ground of a rider on a Ferris wheel can be modeled by the sinusoidal function, and they give us the function, where h is the height of the rider above the ground in meters, and t is the time in minutes after the ride starts. So similar to the last one, right? But now this time it says, when the rider is at least 11.5 meters above the ground, she can see the rodeo grounds. During each rotation of the Ferris wheel, the length of time that the rider can see the rodeo grounds to the nearest 1/10 of a minute is. So let's graph this and see if we can get our bearings here. So here, I'm just going to pause it and then throw that into my graph, or my calculator, I mean. Okay, so make sure that you've typed yours in the same way that I've typed mine in to make sure that you're doing this right. And again, make sure it's in radians. Okay, so then we'll graph this. I've still got the same window setting as last time, which actually looks pretty good. Okay, so now it says that she can only see the rodeo grounds when she's at a certain height. All right, so what I'm after here is, well, let's figure out that height. So what I want to do is, so when it says the rider is at least 11.5 meters high. So that means my h is 11.5 meters high. What I'm going to do here is graph a line at 11.5. So let's do that. So let's graph one more line at 11.5. Okay, and then we'll do it. So we'll graph that. So then we can see a line kind of cutting off the top of this, right? So it's actually up here where she's able to see the rodeo grounds. So really what I want to do, if this is my time going past, right? What I want to do is figure out the length of time from, let's say, like this spot, we'll do the first one, like right there, to right there, right? I want to figure out that time. So what I'm going to do is I'm going to figure out where this thing crosses here and where it crosses here, and then subtract those two x values. Okay, so let's find those intersection points. So I'm going to go second calc, and then I'm going to find intersection, so 5. And then let's find those. So the first one here. So again, I'm going to go first curve, right? So I'm on the blue one. I say yes. And then it's onto the red curve and it says, do you want to figure out this one? I say yes. Take a guess. Yes. All right, so that first intersection point is going to be at the point 2.08 yada yada, and then y is equal to 11.5, which makes sense, right? That's the height of that one, right? So let's write that one down, okay? So that's going to be at 2.088. So it's going to happen at a time of 2.088, okay? So that'll be like our time 1. So now our time 2 will be, so we'll just do the same thing, but now we're going to do it for the second spot. Okay, so we'll move over to the next one. So we'll go second, calculate. We're going to find an intersection again. Let's move it on over to that one. So first curve, yes. We want us to find the second curve there. Take a guess, yes. So that one's going to happen at 3.89. 3.89. Okay, so the amount of time that she can actually see it is in between those two times, right? That's the time that she's above. That's the time that she is, above there, right? So then we just subtract those two. So this will be, maybe I should have left one more digit there, 3.894. So we have the same number of decimals. Okay, so then we'll just plug that into our calculator. So we got 3.894 minus 2.088. So 1.8 seconds. Not seconds, minutes. I thought that was pretty short. 1.8 to the nearest tenth of a minute. So yeah, 1.8. Okay. All right, so let's do this one. Let's make a sketch of this. So it says a Ferris wheel has a radius of 12 meters, and its center is 14 meters above the ground. A rider gets on a chair of the Ferris wheel at its lowest point and completes one full revolution in 52 seconds. All right, so sometimes it's helpful to actually make a bit of a sketch of this. So if this was our Ferris wheel, okay, so they're saying this thing has a radius of 12. And its center is 14 meters above the ground. So really, what that's telling us is that our midline would be at 14, right? So I know that this thing is going to go up and down around 14. So that's kind of a good place to start, right? I also know that this thing is we're going to get on at the bottom, right? And if we get on at the bottom, then that's going to be 14 where we started, and then minus 12. So I'm going to be getting on, are you guys okay with that, at 2? So that's going to be like the beginning of our cycle, and then I'm going to imagine that this thing is going to go up and then back down again, okay, because that's what our sine waves do. Now, it says that the next one that's going to be important is it says that it does one full revolution in 52 seconds. So what we could do is say, okay, over at 52 seconds here, I know we're going to be back where we started. So it's going to go up and then back down again, okay? Now, the other point that might be worth plotting, and probably is, would be, well, right in the middle, right? Because if this is one full cycle, and I'm imagining that this thing goes up and then comes back down again, I'd like to know where the top is. That would be helpful. So the top is going to happen right in between those 2 points, right? It'll happen half of the period. So that's going to happen at 26. So where would that be, right? So I know the x value would be at 26, but how high am I? Well, I know I'm going to be my radius high, right? So I'm going to be that far off of my midline, so another 12. Okay, so I can just really go 14 plus another 12 here. So we're going to be up at 26. And then, so that's the way my graph is going to look. And then let's use the actual tool here to figure that one out. So, so make sure we're using the right. You guys will see that there's 2 different ones that you can choose. I think it's probably going to be the best to use, yeah, this coast like this one where it goes from like you can see the bottom to another peak, instead of this one where it starts in the middle of the wave. You can see that like dot up until the peak, because yeah, it's kind of nicer. We know we start at the bottom and then we go up to a peak there. So yeah, that's pretty much it. My drawing kind of was messed up there, so here I'm going to clear that and go to my tool. Okay, so we want to use this one. We'll start at 2. And then at 26, we know we are going to be up at 26, we said, right? And just double check. You can see, okay, are we actually at 52 for one full cycle? And yes, we are. So that should be our graph of that one. All right, let's do this toy car one. So an electric toy car is traveling around the circular track at a constant speed. A ruler is positioned beside the track as shown in the diagram. The position of the car measured in centimeters with the ruler can be modeled by the sinusoidal function, and they give it to us here, where P is the position of the car in centimeters and T is the elapsed time in seconds. All right, so the amplitude of the sinusoidal function is, okay, well, you know what? I'm going to let you guys figure that one out from the lesson, so I won't give you that one. But I have a feeling that the second part might be a little bit tricky. So it says, and the time it takes for the car to travel around the track once is. And why I say that might be tricky is just figuring out what they're actually asking for there, right? So if time is what we're measuring this in, and it wants to know the time around the track for one full time around the track in seconds, what it wants to know is the time that this thing goes around here to here again. That would look like this. Like if we were doing a wave, that would be the time for it to go up and then back down again, like one full wave, right? So it wants the period, is kind of what I'm getting at here. Okay, so we got to find the period. So remember how we find the period. Period is equal to 2 pi over b, right? Or b is equal to 2 pi over the period, but either way. But we're looking for p. So now I just fill it in. P is equal to 2 pi, and then b, remember what b is. B is the number out front of my x or my t. Okay, so this is going to be over, and then pi over 6. Okay, now I got a fraction over a fraction, which can be a little bit confusing, but that's okay. Just remember that when you're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So I'll just go 2 pi times, and then instead of pi over 6, it's going to be 6 over pi. And that works out well because now I've got pi on the top and pi on the bottom. Those pi's cancel. And we just get 2 times 6, so 12. So our answer here would just be once every 12 seconds. All right, so I think that's all the ones I'm going to go through. I'm going to let you guys kind of try the rest of them if you haven't got there yet. So yeah, that'll be it.